Tonight's Chapter 6, Local Area Networks. So, outline, we'll start out, we'll talk about some of the LAN components. Hardware, some of the software, some of the various components, cabling, etc. We'll talk about traditional Ethernet, which is not really seen all that much anymore, but it is kind of important to talk about just a little bit in the sense that it shares some commonality with wireless networking, for example. So we'll talk about that a little bit tonight, and then a little bit more when we talk about wireless. Then we'll talk about switched Ethernet, which is more what you see today. The chapter finishes up talking about best practice LAN design and improving LAN performance. Improving LAN performance is probably something you want to pay a little bit of attention to as you're going through the chapter. It shares a lot in common with improving performance in a WAN environment as well. So it's some consistent stuff. So if you learn it once, it'll apply to some of the other environments. So why do we use networking? Why do we use LANs? Well, it really comes down to sharing resources in one fashion or another, whether it's information or it's hardware. Information sharing we do in order to hopefully be able to make better decisions. If we're all basing our decisions off a common set of data, we're going to spend more time making sure that that data is correct, that information, that data is consistent. That means we're all able to make better decisions, hopefully, based on that type of information. Hopefully end up with better decisions. Sharing resources, things like printers. We don't have to have a printer for every computer in the room. We share one printer in the back. That way we don't have to invest in one individual printer. So we can save money by sharing resources. We can share other things as well, internet connections, things like that. So we end up reducing our costs that way. We can also share software. We don't have to purchase the same software for every single computer. Rather, we can load the software on a server and share it amongst all the computers individually. They kind of go through an example down here where you might have a total of 30 clients in your organization. You can invest in a word processing package like Microsoft Word for all 30 machines if you want. But what are the odds that all 30 machines are going to be are going to need Microsoft Word at the same time? Depending on the type of office, you may or may not actually need that. So you can actually go through a process of purchasing a 10-seat license, which basically means any 10 computers could have it up and running at one point in time and still be legal, still be complying with the license agreement. That's done through a process called LAN metering, which basically is the process of limiting the number of copies or the number of workstations that can be running it at any point in time. So it allows an organization to provide that software to all the various workstations that need access to it, but limit it with respect to your license agreement. It makes it very easy to provide all 30 of those workstations have access to Microsoft Word, just not all at the same time. So it keeps track of the users, prohibits using more copies of the package than are licensed. You're trying to help minimize copyright violations. That's the idea behind it. And as you can kind of see from that, 40% of software used in the world is illegal. It represents about a $40 billion loss. So it's a pretty significant amount of money that's going by the wayside. So software companies certainly have an interest in that. This book is a couple of years old, so you can bet that number is higher today. So there's a lot of different ways of looking at networks and categorizing networks depending on how you want to look at it. One of the common ways is either a client-server network or a peer-to-peer network. That's a common way of looking at networks and distinguishing one from the other. So that's what the next few slides are talking about, distinguishing between those two based on that type of category. So a dedicated server network involves the use of one or more servers to be able to serve up something. Serve up web pages, serve up email, serve up files. The server can provide a variety of different things. An individual server can provide multiple services, or you can have multiple services providing individual services depending on the size of the network. It tends to be a very popular approach to networking because it provides you the ability to really secure a lot of your data, centralize your data, which facilitates backing it up, protecting it, provides access control, so people have to log in and have authentication to prove that they are who they really say they are. Authorization, that they're allowed to read files, delete files, add files, etc. So it gives you a lot of capabilities with respect to that in a client-server environment. You don't get that in a peer-to-peer network. In a peer-to-peer network, you don't really have any dedicated servers. You still have servers. The difference is that every client or every machine on the network is both a client and a server, or has that capacity. They can be both at the same time. So you don't have that centralized capability of managing your network. It becomes much more difficult to manage files. So say, for example, we're all on a peer-to-peer network in class here. Sanjita has a file that she's working on, and she stores it here, and somebody else decides to work on that file. They copy it to their local machine and work on it and save it. Well, now, unless everybody else knows that that file's been taken somewhere else and saved, and that's a different version of the file, now we've got two different copies of the file, and they're not in the same state. So managing those files becomes much more difficult in a peer-to-peer network. So that's one of the downsides to it. But it's cheap. Most operating systems have the capability of implementing a peer-to-peer network without doing anything extra to it in terms of buying any additional software. It's usually built in. You just have to configure it. Peer-to-peer networks are easy to configure. So in small environments, home environments, small office environments, it makes sense to implement a peer-to-peer network. But as you grow as an organization, you've got to switch over to a client-server environment. It makes much more sense. Any questions so far? Yeah.
If we the LAN metering you told us, in that, if they have 10 licenses, and what happens if the 11th person is trying to open?
It depends on the metering software. Originally, metering software really only allowed you to identify how many people were using the software at any one point in time, and it would basically log that activity. Really, over about the last probably 15 years, or maybe a little bit more than that, metering software actually allows you to clamp down and say, when that 11th person tries to log in, it will deny you access. It will tell you that all the licenses are already currently in use. You'll have to check back later. And that's normally what you see anymore.
And if, like, we have 10 licenses, so every user has their own username to log into that software, or?
It's usually handled through something like Active Directory. So it's not a case of you as an individual having to do anything extra other than logging into your individual workstation. The metering software keeps track of, we've already got 10 users on the system that are already using the application. When that 11th person logs in, regardless of who they are, when that 11th person tries to run that application, then it sends that message out. The system administrator, if you say all of a sudden you realize 10 licenses just isn't enough, we need to buy 5 additional licenses, the only thing that really has to be done is the system administrator, they make that purchase of 5 additional licenses, then the system administrator goes into the metering software and bumps that number up from 10 to 15, and then nothing else has to be done on the client end because it's all being run from the server.
So is it an example of thin client usage?
No, I wouldn't say that that's an example of a thin client because the application, usually when you have that type of environment, you still have a client that's loaded on the individual machines. It's just not, that client's not capable of in the case of, say, Word, it's not capable of firing all the way up and being able to create documents. But you still have to have a client on the machine that's accessing the server. So dedicated server networks requires one or more dedicated computers or servers, permanently assigned a specific task to provide web pages, to provide access to a file, to provide access to a printer, and it enables users to share files, printers, etc. May form a powerful enterprise network replacing mainframes. That depends. There's still a place for mainframes for certain applications, but certainly a lot of times where organizations really kind of require the use of a mainframe, instead in a lot of cases they're able to use what's referred to as a server farm, multiple servers or lots of servers to be able to take the place of that mainframe. So it really depends on the organization as to whether or not it replaces a mainframe and the uses that they need. One of the real advantages to using a server farm over a mainframe is the scalability of it. With a mainframe, mainframes are obviously very expensive. They're also very expensive to upgrade. There's no such thing as a little upgrade to a mainframe. It's usually a really expensive upgrade. And that produces a lot more capability when you do that upgrade. As opposed to a server, if you've got a server farm, you can, for a relatively small amount, simply add another server, and you've increased your ability to serve whatever it is you're serving a little bit. So the scalability of servers is much better than it is for mainframes. Server software runs a server network operating system. Examples include Windows Server 2003, 2008. I think they've got Windows Server 8, which is kind of a code name for their up-and-coming server release. Who knows what it's ultimately going to be called. Linux, Solaris for Unix and things like that. Also requires special communication software to enable communications with clients. This is something that's built into the operating systems, the server operating systems, the clients as well. It's not something you have to add on additionally anymore. Wasn't always the case though. Types of dedicated servers: web servers, email servers, database servers. Those are probably some of the more common ones. You think of a web server all the time, you hear that terminology. You hear about email servers fairly often. You hear about database servers periodically, print servers periodically. But there's all kinds of servers. Probably file servers are one of the most common. What type of files might a file server serve up? Word files, Excel files. It's essentially a repository for the various files that users in an organization might need. One of the advantages to using this approach, again, as opposed to a peer-to-peer network, you can restrict access. Restrict access doesn't mean you simply deny access to certain users. It means you can deny access. It also means you might say somebody can read a file, but they can't delete it. Some people need access to be able to read the contents of a file, but you don't want them to delete it. You don't want them to be able to do that. They may have the ability to create new files, and other people may not. So you can really, especially with a good network operating system such as Windows Server 2008, there's a lot of granularity, a lot of customization that you can do and allow or not allow users to do. Print servers basically allow a server to control access to a printer. To assign print jobs based on priority, to allow print jobs to occur by certain users, or certain types of jobs to occur at certain times during the day. Why is that important? We'll come back to that later on in the chapter, but it allows you to shift some of your network usage around the network when perhaps the network is being overused at one point of the day and it's less used at another point. Maybe you want to shift some of that usage around. The use of a print server allows you to do that. You can create certain rules that will allow you to do that. Peer-to-peer networks, on the other hand, don't have that dedicated server. So any client, or any computer, I should say, on the network can act as both a client and or a server. How? Right-click on a folder and share it. So it's really very easy to set up. Appropriate for small networks. Once you start to add too many computers to the network, though, it can get really confusing about where your files are, controlling access to them. Why is it more difficult controlling access? Because the use of passwords to protect files on an individual computer is exactly that. It's on an individual client. So on this computer, if you wanted to protect the files, you would password protect the files on that computer. But that doesn't do anything for the files over here. So you have to implement it on each individual computer. In a client-server environment, all that's handled on the server side. So you manage all that security at one place. So it's a lot easier to manage there. Having said all that, why do we use peer-to-peer networks? They're cheap. It's easy. So it definitely makes sense. Usually smaller organizations, when it comes to IT, are what's referred to as resource poor. They don't have a lot of resources. They don't have the technical know-how. They don't have the monetary budgets relative to their larger counterparts who do have those resources. So as a result, a lot of times small organizations, home networks, they run in a peer-to-peer environment. A disadvantage, they tend to be slower than dedicated server networks. Why? A server is, the server operating system is optimized to be able to provide those files, to provide access to web files, email, etc. So it tends to perform better than in a peer-to-peer environment. And that difficulty in managing. Again, you open files from different locations, it's hard to keep track of where the most recent file is. You've probably done that yourself just by emailing files to yourself. You make changes in one location, you've emailed that file somewhere else, you work on another location, and you have to keep track of which one's the most recent file. Any questions so far? Or yet? Not yet, but now? Yet. Since the last time. Okay, so basic LAN components. Obviously, your client and your network server, the computers, things that you're used to seeing, used to interacting with. Your client computer, you've got your system unit, your monitor, your keyboard, all the basic stuff that you would expect. You've got your network wire, whether it's twisted pair, coax cable, fiber optic, wireless. You've got to have some method, some medium to be able to transmit signals across. Whether it's a wire or wireless doesn't really matter. You've got to have some kind of network card, something for that wire to plug into, or something to send and receive those radio signals. So that's referred to as a NIC, a network interface card, a network adapter, things of that nature. Those are going to be plugged into something, at least in most situations, they're going to be plugged into something. A hub, a switch, a router. Hubs you're not going to see all that much anymore, but they do exist, and we'll talk about those a little bit more here in a little bit. And then on the other end, it's pretty much the same, some type of medium, a server, again with a network interface card plugged into that one. So what are NICs? They get called all kinds of things, network adapters, NICs, network cards. Contains physical and data link layer protocols. A NIC really operates at the data link layer. That's layer 2 of the OSI model or of the Internet DoD model. But it also tightly integrates with the physical layer. Why? Because that cable operates at the physical layer, right? Twisted pair. Well, that cable plug has to match exactly to the plug on the network card. If it doesn't, you can't connect the two. So there's a very tight integration between the network interface card at layers 1 and 2. A network card includes a unique data link layer address. So it's kind of like an IP address, but this is something that's a hardware address. So the IP address is a logical address to the machine. Logical is something that you can set. This is a hardware address. It's set in the ROM, the read-only memory of that network interface card. There's two parts to that address. The first part identifies the manufacturer of that particular network interface card. The second part identifies a unique address for that manufacturer. So the right-hand side of the address may be duplicated with other manufacturers, but the left-hand side of the address is going to make that be unique across because it's different for different manufacturers. So every network interface card on a segment has to be unique. The reality is there's not supposed to be any duplications anywhere in the world, but the reality is that there are, and so every now and then you'll run into some kind of a conflict, but that's pretty rare. Network interface card includes a socket allowing computers to be connected to the network. That's the plug where the network cable actually plugs into. That's all they're talking about there. And its responsibility is to organize data into frames that sends them out onto the network. So it's the process of actually taking those various ones and zeros that you're trying to send across the wire and placing those onto that wire. In a lot of cases, traditionally, it was a network interface card was a separate card. It was plugged into an expansion slot in the PC. But today, most of those network interface cards are built onto the motherboard. So if the network interface card goes bad, it's your motherboard that's bad. So you either need to add, using an expansion slot, a network interface card, or replace your motherboard. Or you can end up getting one that plugs into a USB port, which is not all that common. Is everybody good on network interface cards? So, what plugs into those? Some type of network cable. It's got to be a cable that's compatible with that network card. You're not going to plug a coax cable into a UTP network interface card. It doesn't work. So the cable is used to connect the computer physically to the network. These are some of the common types of cables. Unshielded twisted pair, which is by far the most common. It's cheap, it's easy to install, it's very flexible, so it tends to be preferred, and it performs very well. You've got shielded twisted pair, which doesn't get used as often. It's preferable in terms of performance because it's shielded, so you're going to have less interference. But it costs quite a bit more, and it doesn't bend quite as easily. So as a result, it's not quite as popular. Fiber optic is another cable that can be used, high capacity. It's becoming more popular, but relatively speaking, it's still expensive. So unless you have a specific application for it that calls for fiber optic, that you need that speed or that you need the security that gives you, in a lot of cases you don't use it. One that they left out was that at one point was fairly common was coax cable as well. It's similar to the coax that you see at home in your televisions, and it's the same type of cable, generally speaking, and that's one that they didn't include. You don't really see it used hardly anymore, so that's probably why they left it out. So where do those cables go? They got to go to some kind of junction box to tie all those various things together. They talk about hubs and switches a little bit here, and you're going to see that throughout the rest of the presentation because they sit at the same point logically in your network, but they perform different functions, hubs versus switches. So a hub or a switch acts as a junction box linking the cables from several different computers. Usually they're going to have 4, 8, 16, some multiple of 2 as far as the number of ports. So 4, 8, 16, 24 ports are really pretty common. May allow connection of more than one kind of cabling. For example, you may have a switch that will allow you to connect not only unshielded twisted pair connections, but also coax cable or also fiber optic. That is not all that common until you start to get into more commercially grade equipment, but those are certainly possible. If you remember from the signaling techniques that we talked about before, we talked about the distinction between a repeater versus an amplifier. We're talking about digital data, so these devices repeat the signal. That means that when a signal comes in, if that signal is slightly damaged, it allows that signal to be regenerated and reproduced exactly the way it was originally broadcast. The reason that's important is that extends the length of our segments. So we may have, say, a client that's over here. We may have a switch that's right here, and this may be 100 meters. Well, we may have another client that's way over here that's connected. If we pick up a little bit of interference right in here, our signal is slightly damaged. But assuming it's not too damaged, our switch here can regenerate that signal so that it comes out exactly the way it left our original host. So that's an important feature of these types of devices. It allows you to exactly copy the way it was sent originally. The difference between that and an amplifier is just going to take that noise and amplify that noise, that interference. So it's one of the differences between an amplifier versus a repeater. So yeah, it helps to extend the maximum LAN segment length. Planning for LAN installations. Why is it important? LANs grow really quickly. They do, demand for them. If you give somebody a really high-speed network, they will figure out a way to use that bandwidth. They just do. So it's a lot easier in the initial design of that network to build in extra capacity up front. It's a lot more expensive to have to come back after the fact and add capacity. So that's what they're talking about here. They really want you to install 20 to 50% cable, more cable than you really need at a particular point. At this particular point, why? Because by the time you get it constructed and it actually goes into use, demand is going to rise quickly. In some cases, you may want to double that number. Network operating systems. Any questions? What we've covered so far? Network operating systems. There was a time where operating systems did not have a network operating system built into them. What did that mean? That meant that you had a server product that was capable of serving up various files, but DOS, for example, or early versions of Windows, for example, did not have the ability to log into that network or connect to that network. You had to load a client on top of that to be able to access that server. Anymore, network operating systems are part of our operating system, and we tend to take those for granted. But there is a separate part of the operating system that handles network operations. So parts of the network operating system, you've got part of the server that addresses network connectivity. You've got part of a client on the client computers that handles network connectivity. You've got network profiles and directory services. In the next few slides, talk about each one of those. So directory services are basically a phone book, if you will. So think about a phone book, what you use a phone book for, assuming you don't use Google to look up names and numbers anymore like everybody else. Phone book gives you a way to find somebody's address, to find their phone number in a very logical fashion. And that's what a directory service is. It's something that allows you to find various resources that exist on your network in a very kind of a tree-like structure. So the locations of various printers, the locations of various directories that you might need. It's a logical layout of the various services that are available on your network. Profiles are basically something that is probably easier to understand when I talk about user profiles. When you log into a computer for the very first time, you have a user profile that's generated. What does that user profile consist of? It consists of things like your home directory. It consists of all the various subdirectories that belong to that. It consists of all the various drives that you have networked for your particular user profile. So it's kind of a description for you. The reason the use of user profiles is important is as a network administrator, you create a generic user profile for, say, salespeople. That's important because when you have a person added to the sales group, it generates that profile automatically based on that profile, or generates that user's profile based on that group's profile automatically when they're created. So you have a lot of consistency. Every time another salesperson is added, they have exactly the same profile. If you didn't do that, every time you added a user, you would have to have a checklist, or whether something that was written down or a mental checklist, and manually go through the process of creating all those directories, mapping their various drives, giving them authorizations to the various folders and files, etc. that you need to. What's the problem with that? You're going to forget something. And so it's a bit of a security issue. So the use of profiles is a really important technique that system administrators can use to have some consistency in how their various users are set up on the network. Network operating system server software enables servers to operate and handle all the network functions to be able to pass the data that it needs to up and down the internet model protocol stack. So taking that request at the application layer, when it receives a request for a web page, the web server knows I need to respond with an HTTP packet that includes that web page, right? And it passes it down the network layer, the data link layer, etc. That's what the network operating system's job is, to handle all that. Replaces the normal operating system on the server. I say replaces the normal operating system. It's part of that operating system in today's networking environment. So some examples of network operating systems for server network operating systems: Windows Server 2003, 2008, Solaris, Linux, Unix, etc. On the client side, the client network operating system does a lot of the same stuff. It's not really serving up web pages or anything like that, but it still has to be able to take a web request and say, hey, I want this particular page from a web server, and it still has to be able to process that and put that down onto the wire for the network to pass across the network. So you still have a lot of the same stuff, it's just operating in reverse. Included in most operating system packages anymore, what I was talking talking about earlier, you used to have to add a client to your operating system. The network operating system, part of the operating system, is built in anymore, so it's not something you have to add anymore. And it allows the client to view and access available resources, so you can browse around the network and look at what's there. That's what part of the responsibilities of the network operating system on the client side of things. How are we doing? Clear as mud? Okay, so we've passed those signals. We have a web request from a client to go to a web server. We got to place those signals onto the wire. How are we going to go about doing that? Well, the most common protocol, or language, if you will, is Ethernet, used by almost all LANs today. The book doesn't really talk about the other ones. There are other protocols that are used at the data link layer. Token ring, for example, is a common one. But by far, Ethernet is the most common. Originally developed by a consortium of Digital Equipment Corp, Intel, and Xerox. It's actually developed in large part by Xerox. Xerox really developed a lot of the stuff that we tend to take for granted today. They didn't capitalize on it, and that's why they're Xerox and not IBM and some of these other companies. But they certainly had some very high-end engineers working for them back in the late 60s. Ethernet protocol was standardized as IEEE 802.3. So when you hear 802.11 that you normally hear in the wireless world, that's just a working group that works on the wireless standards that we use in wireless networking. This is exactly the same thing, it's just dealing with Ethernet specifically. Types of Ethernet, there's a couple of different categories. There's been different versions over the years, but one way of looking at them at Ethernet is whether or not it's shared versus switched. You don't really see shared Ethernet anymore, but this is what I was saying at the beginning of class. It's worthwhile going through what shared Ethernet is, because wired Ethernet works very similarly to shared Ethernet. Most networks today, you're going to see switched Ethernet. We'll talk about both of these over the next several slides. Something else before we actually get to that is this concept of topology. Topology is the basic geometric shape or geometric layout of the network. This book does a good job. There's a lot of network books that don't separate physical versus logical topology. This one does actually talk about it for just a little bit. So logical topology refers to how the network works conceptually. How's the data going to go from point A to point B conceptually? And we'll show you an example here in just a little bit. Versus the physical topology, how the network is physically installed. So shared Ethernet's logical topology can be viewed logically as a bus topology. And I'll show you a network diagram in a second that I think really helps to illustrate that. With a bus topology, all messages from any computer flow onto the central cable or bus. A computer receives messages from all other computers. That's the part I want you to remember out of that. From all other computers. Whether the message is intended for that particular computer or not. What's that mean? It means there's a lot of traffic. There's a lot of attention that the various clients are having to pay to on the network. When a frame is received by a computer, the first task is to read the frame's destination address to see if the message is meant for it or not. So everybody has to listen. Oh, that's not for me. It ignores it, except for the one that it's actually addressed to. So logically, for shared Ethernet, it has a bus topology. So when this computer sends a message out, it hits that wire, that message goes there, 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 and there to every computer on the network. They all ignore it except for the one that it's actually addressed to. The physical topology, though, may be right here, may be represented differently. Anybody want to take a stab at the physical topology that we're looking at there? It's a star topology is what it would be referred to as. It's not quite a star. It'll look like a star because they're not all around it, but it looks like a physical star topology. And that's what you end up with shared Ethernet. Shared Ethernet has a bus logical topology, but a star physical topology. If you want to expand the network, let's say you've got different locations, you may want to have 2 hubs. Well, that's great, but what happens when this one wants to send out a message? This one gets it, this one gets it, this one gets it. It goes to this hub, and this hub does the same thing. Sends it to this one, sends it to this, sends it to the printer. They all ignore it, except for the one that it's actually addressed to. So you can start to imagine as you add more and more clients to the network, the network gets really busy really quickly because that message is going everywhere, regardless of whether or not it needs to. So they have to have some way of managing access to that wire. We can't all be talking at the same time. What if this one wants to send a message and this one wants to send a message at the same time? You've got to have some kind of access control mechanism to be able to handle that. And that's what this is referring to right here. Carrier sense multiple access collision detected. This is something you probably want to make sure you nail down. It's similar, there's something similar to it in the wireless world that we'll talk about when we get there. Everything's exactly the same except for the collision detected part. It's collision avoidance in the wireless world. So, the next slide or two, I think, talks about this in a little bit more detail, so I'll come back to that in just a second. But frames can be sent by 2 computers on the same network at the same time. That creates a problem. They can collide and destroy each other. It can be termed as ordered chaos, and it tolerates rather than avoids collisions. That's this CD part, collision detected. Tolerates rather than avoids collisions. So rather than trying to actually avoid collisions, it tolerates it. How does it do that? If a collision is detected, it simply resends the signal, or resends the same frame again. So it has a way of correcting once a collision is detected. So the different parts of carrier sense multiple access collision detected. The carrier sense part, when you have a message to be sent across the network, the first thing that's going to happen is the network card is going to listen to the wire. Is there anything else going on? Is any other computer on the network talking at this particular point in time? If there is, it automatically stops and waits for a random amount of time. Now, we're talking computer time here, so it's a fraction of a second. It's not much time at all. But it waits for just a fraction of a second, and then it starts over. Is there anything going on the network? Once it determines that there's not anything going on the network, it's going to go ahead and start transmitting. If there's a problem, it detects that there's multiple access. Whoa, wait a minute. Somebody else happened to transmit at exactly the same time. We've got a collision. We've got to stop for a random amount of time, again, computer time, so it's a fraction of a second. We'll stop for a fraction of a second and then retransmit that frame because it's been damaged. So that's the carrier sense multiple access collision detected. That's how it handles media access control in a shared Ethernet environment. What are the wires that it's sending this across? This stuff applies to both shared Ethernet as well as switched Ethernet, so there's not really much difference. But why they threw this part in right here, I'm not really sure. It kind of breaks up the discussion a little bit, but they did, so we'll talk about it. 10 base T, an older standard. You won't see that on modern networks. If you run across 10 base T, recognize that you're looking at an older network. Cat 3 and Cat 5 both work. Really inexpensive. Actually, it's probably expensive at this point because it's probably hard to find. The downside is if you run across it, you're pretty much guaranteed that you've got to replace the cabling. Why is that important? We already talked about replacing that cabling after the fact is expensive. You prefer to initially have very high-end cable because that's the most expensive part to replace. Runs up to 100 meters and rapidly losing ground to 100 base T, which is sometimes referred to as fast Ethernet. Go back for just a second. When they say 10 base T, the 10 part, they're referring to the speed of the network. So that's 10 megabits per second. The T refers to twisted pair. By far, this is the type of mechanism that you're going to see, the type of designation that you're going to see. 10 base T, 100 base T, things like that, because Those are the most common types of network infrastructure that you're going to run across. Now there's 1000 base T for gigabit Ethernet. So same thing for 100 base T. You can probably kind of guess based on that name. It runs at 100 megabit on twisted pair on that particular network that they're describing. You really need Cat5 cable and up, so better quality cable. Also referred to as fast Ethernet. Replace 10 base T in sales volume. Even 100 base T today is probably starting to wane. Why? Because the book's a couple of years old and gigabit Ethernet has really come down in price. So you're seeing a lot of newer networks taking advantage of gigabit Ethernet. The advantage in some cases is you can have 100 base or combined networks, which is a really advantageous to system administrators. Why? Because they don't have to go out and replace everything on their network. If they weren't backward compatible, if you decided to go to 100 base T, you'd have to go replace every network card on your network with a 100 base T network card. That, may not be feasible cost-wise. So in some cases you can combine 10 and 100 megabit networks together. We'll talk about that a little bit more when we get to switches, what facilitates that, what allows that to happen. But keep in mind, you don't necessarily have to have one or the other. You can have a shared environment.
Sorry,
Yeah.
can we go back once?
Sure.
Okay, so if you have 100,
Uh-huh.
you can use 10. Is that what you mean by, yeah?
Yes. You can't have 10 and have 100, but you can go
Can have-
backward.
Okay, okay.
Now, when we get to switches here in a little bit, and I'll explain why that's possible, how that actually works. Okay, so you've got gigabit Ethernet as well, same designation, 1000 base T. If you happen to be using coax or fiber, the T would be different. They have different designations for different media. So the T again says it's for twisted pair. Maximum cable length, again 100 meters. They say Cat5. I don't believe that's actually correct. I think that actually has to be higher than that. I think 5E minimum, Cat6 and above. And then you've got fiber optic base that you can run the gigabit Ethernet across as well. And this is what I was talking about, 1000 for a gigabit, LX for fiber optic. And you get better distance that way. Here's another type of fiber optic, 10 gigabit Ethernet and 40 gigabit Ethernet. So you're really seeing a lot of the speeds get up there, and that's the way it's always been, and that pace of change is just getting faster and faster. So then they kind of give you a comparison of the different speeds and the different network types. The ones I really want you to be familiar with are really those top three. When you start to see some of these other ones, I'm less concerned, other than that you know that those are fiber and that they run really fast. So we talked about shared Ethernet, and one of the problems with it, that not everybody can talk at the same time. It's the same thing in the class. If you all talk at the same time, nobody's going to understand anything. Switched Ethernet is a different approach. Switched Ethernet says we have to have some kind of method of only allowing one person to talk at a time, or perhaps a better way of putting it, that when one person talks, it doesn't interfere with somebody else talking. And that's what switched Ethernet does. Uses workgroup switches designed to support a small set of computers, 16 to 24. It's the same general idea as a hub. All the various devices connect into it. In fact, a switch and a hub may physically look identical. Unless it says switch or hub on it, you may not be able to tell the difference just by looking at them, because the plugs are going to be exactly the same. It's what goes on inside the device that actually makes the difference. Designed to support a group of point-to-point circuits, so no sharing of circuits. Point-to-point, what does that mean? That means this computer to this computer, or this computer to that computer, but not this computer to all these computers. It supports those connections individually. So the logical and physical topology of the network becomes a star topology. They're exactly the same with a switched network. That works with the switch reading the destination address of the frame and only sending it to the corresponding port. So if this particular computer that's plugged into this particular port has something that it needs to send to the computer that's plugged into this particular port, the switch, through what we'll get to here in just a second, said when it receives that information, instead of sending it out on all these other ports, it only sends it out on the port that it's being addressed to. So it allows all these other ports to go ahead and continue to communicate however they need to continue to communicate. It does that through the use of a forwarding table. It keeps track of what computer is plugged into what port. How does it keep track of which computer is which? Remember that MAC address we were talking about earlier? That hardware address, the network interface card? It reads that information of those frames as they come in. It keeps track of that and which port that MAC address is associated with. So it keeps that routing, it keeps that information, that port and that MAC address, into a routing table or a forwarding table. It lists the Ethernet address of the computers connected to each port. When the frame is received, the switch reads its layer 2 data link layer destination address, so that MAC address, and then sends the frame out of the corresponding port in its forwarding table. So, for example, you want to have a forwarding table that's right here. You've got a switch that has 4 ports on it. Port 1 has this MAC address. Port 2 has this one. Port 3, etc. So when port 1, or the server over here needs to send a message to, say, computer A, it sends it to the switch. It reads it, and it reads that this request is for this particular MAC address. So the switch says, okay, what port is this particular MAC address plugged into? It goes over to its forwarding table, reads that information, says, oh, that's port 2. So it sends that message out, port 2, to the client. That leaves port 3 and port 4 free to talk as much as they want. It's not going to interfere with that communication. How does that table get populated? Probably a reasonable question. You don't have to do anything. Switches are smarter than hubs. Hubs just a dumb terminal, basically. Just information goes into it and goes out of it. It doesn't do any analysis at all. The switch actually does do a little bit of analysis to it, and it starts out as a hub. But as the data starts to come into it, it reads that information and populates that forwarding table automatically. It's not something that you have to manually do. So modes of switch operations, not all switches are created equal. This goes back to what we were talking about just a minute ago. How does that actually work? You've got 3 different types of switches. Cut-through switching, which doesn't really get used all that much. Cut-through switching is a very fast approach. You don't have a lot of analysis. What happens is the packet starts to come in on one port of the switch. The first part of that packet consists of what? Header information. The source address, destination address, all that type of stuff. Then you've got your data, and then at the end of that packet, you've got correction information. You know, there's this packet is damaged or this packet's not damaged. With cut-through switching, what happens is the first part of that packet starts to go through the switch. The switch reads that information, the destination address specifically, and says we need to go out this other port. So it starts transmitting immediately. That's great, right? It's very fast. That's true, but the information that says that packet is either good or not good is at the end. So in some situations you actually end up transmitting bad packets. So that's one of the downsides to cut-through switching. It's very fast, but you can potentially be broadcasting bad packets. What you more commonly see is store and forward switching and fragment-free switching. One of the real advantages to each of these is it allows you to have different speeds on your network that operate at the same time because they have memory built into those particular switches. With store and forward switching, the switch takes a little bit more time to receive the entire packet. It stores that packet in memory because it wants to wait till the end of that packet gets into the switch so it can check the error information. Is that packet okay? If it is okay, then it goes ahead and broadcasts it out or sends it out on the port that it's supposed to go out. The advantage to that is that because of the memory, it now has the ability to, say, take a message from a 10 megabit side of the network and then send it out on a 100 megabit side of the network port, or vice versa. so it's able to handle different speeds. Fragment-free switching is similar, but instead of waiting to get the entire packet, what it does is it does some error checking just on the header information. So once the packet starts to come into the switch, once all the header information is inside the switch, it does some error checking on that header information. It assumes that if there's no error on that header information, that the rest of the packet is probably in pretty good shape. And so then it starts to broadcast it. So it's kind of a compromise between these two approaches. But it has better speed and better speed than store and forward, but it still has the ability to do some error checking that cut-through switching does not have. Does that make sense? Any questions on different types of switches? Most of the time you're not going to have an option to adjust a setting on a switch. You're going to buy a switch that has these particular features. And again, most of the time 2 and 3 are all you're really going to see. Okay. So media access control in a switched Ethernet circuit. You still have carrier sense multiple access collision detected that exists in a switched Ethernet environment, but you don't tend to have nearly the problems that you have in a shared Ethernet environment. Nevertheless, it still uses that as a media access control method. Multiple messages can be sent at the same time. Why? Because it's treating each one as a separate circuit, as a separate transmission. It does allow two computers to send frames to the same destination at the same time, assuming you're using 2 or 3. If you're using store and forward switching or fragment-free switching, because of memory, what happens is a message ends up being sent, both computers end up sending messages to the switch at the same time. Memory inside the switch will hold one of the packets while the other packet's being transmitted. So you have the ability to actually send 2 messages at exactly the same time and not have the same issues that you have in shared Ethernet. Which one's better? There's not. They say comparison. There's not a comparison. Once you get up to about 50% capacity in a shared Ethernet environment, your network's going to grind to a halt. 50%, what is that? Well, if it's a 10 meg network, you're talking about 5 meg worth of bandwidth. 100 meg, about 50 meg. In a switched Ethernet environment, you can run up to 95% of the capacity before you really start to see the network have problems. So you're really using much, much, much more of your capacity in a switched network environment. So the first thing you want to do is go to switched Ethernet. It makes sense. And when I say that, unless it's a really old network, it's already going to be a switched Ethernet network. So best practice recommendations. Switched 100 base T. I would probably replace that with gigabit Ethernet at this point. Why? Because most of the cabling that you're going to get on shielded twisted pair is relatively cheap, even at 5E or Cat6 cabling, and that will support gigabit Ethernet. And gigabit switches are relatively inexpensive. They don't cost that much more than fast Ethernet. So it just makes sense to be both switched and on gigabit Ethernet. Cat5e cables, at a minimum, cost is relatively cheap and gives you some room for expansion to gigabit Ethernet. They talk, and I mentioned this earlier, they talk about fiber. And again, unless you have a specific application, I would probably avoid fiber. They kind of advocate going to that if you need to, but I would tell you that unless you have a specific application, a specific need for it, I wouldn't worry about fiber at this point per se. How do we improve LAN performance? Any questions on what we've covered so far? How do we improve LAN performance? This is what you want a section of the text that you probably want to pay pretty close attention to, because it does apply to the WAN environment as well. A lot of the same concepts in a WAN environment that you see in a LAN environment. So throughput, before we actually get to the actual improvement parts, we need to kind of talk about a couple of things that you want to look at. Ways to assess your performance. So throughput is often used as a measure of LAN performance. The the total amount of user data transmitted in a given period of time. It's the data that we're most concerned about. It's not the header information. It's not the error correction information. It's the actual data that we want. So ideally, we want to have 100% throughput. That's great. Now, it's not practical. We have to have header information. We have to have error correction information. But we want to limit that as much as possible and maximize how much actual data that we're getting through. To improve throughput and LAN performance and identify and eliminate bottlenecks, bottlenecks are points in the network where congestion is occurring. So spots in the network that are causing things to slow down. And once we've identified that, then we can go and try to correct that. Some of those places, potential places, are at the server or at the circuit. Is it our circuit that's actually slowing us down, or is it the server that's slowing us down, or is it the client that's slowing us down? It really could be any of them. And there's different ways of finding those out. They talk about client computers being highly unlikely as being a source of the bottleneck. I would tell you that unless you're in a relatively well-financed organization, that is probably more common than the authors suggest. In smaller organizations or organizations that are resource poor, they simply don't have the money to replace clients all the time or on a cycle that's probably as fast as they should. As a result, they tend to run machines a little bit longer than they should. They're older than they should. They become old, bogged down, and they start to run applications that they really weren't designed to run. So they can be the source of network congestion. It does happen. So how do we find out where that congestion is occurring? Well, we can go to the server. The server has a variety of different tools to assess its utilization. How much is it being hit from various clients? If it's really being utilized a lot, that means all that data is getting to the server. All those requests are getting to the server. So that means your server's the bottleneck. So, and we'll talk about here in a second some of the things you can do to improve that. If utilization is low at the server, that means the requests probably aren't ever getting to the server. If the network is performing poorly, that means your network most likely is the bottleneck. If it's somewhere in between there, it may be the server and or the circuits. So it's kind of hard to say at that point. So if it is the server, what can we do to fix it? Well, the first thing that they throw out there is choose a faster network operating system. That may not be a practical choice. Usually your network administrator is going to be familiar with Windows, or they're going to be familiar with Linux. So unless you want to retrain them, or you want to fire them and get somebody who is familiar with that, a different operating system, it may not be feasible to simply replace operating systems. But that is a possibility. You can fine-tune your network and network operating system parameters, such as the amount of memory used for disk cache, number of simultaneous open files, and the amount of buffer space. Those are all things you can do at the server to try to allow the server to adjust or perform better. So adding memory to a server is almost never a bad thing. Servers almost always perform better just by adding additional memory. Hardware improvements, add a second server. Remember we talked earlier about mainframes. It's hard to upgrade a little bit. In the server world, servers are relatively inexpensive. And I say relatively because $10,000 isn't cheap to me, but compared to $100,000 or more upgrade for a mainframe, $10,000 is pretty cheap. So throw a server at the problem. Some servers have the capacity to have multiple processors on them. So add a second or third or fourth CPU. Increase the amount of memory in it. Add more hard disks or better performing hard disks. Maybe instead of, if you've got old IDE drives in a server, you go to serial ATA or SCSI hard drives. They perform faster. And you could potentially add a second network interface card to it. That actually applies to network congestion as well. Going back for just a second, talking about drive performance, especially important since disk reads are the slowest task the server needs to do. Why is it the slowest? Electronics really performs pretty quickly, but traditional hard disks are not just electronics, they're mechanical as well. You've got a physical hard disk that's spinning around. So you've got to wait for the disk to spin to exactly the right position to be able to read or write data to the right spot. You've got a head that swings back and forth across those platters. So that head has to swing to exactly the right spot to be able to read or write data to where it needs to be able to do so. So disks are the slowest part that you have in a computer system. So ways to improve that performance, like I said earlier, you could switch from, let's say you're using IDE, which is a very old type of hard drive, to serial ATA, which is much more common today. Or if you're in a server environment, you should probably be using SCSI anyway. It performs much better. Or you can implement array, a redundant array of inexpensive or independent disks, depending on the textbook that you're reading. Which there's different categories of RAID, and there are different ways of combining multiple drives in order to get better performance. Basically, the way RAIDs are, an oversimplification of RAID generically, might be that instead of writing a file to one drive, an entire file, you might be able to split that file up and write half of it to one disk and half to another disk. Essentially, you're getting almost twice the speed of it because you don't have to spend so much time writing that file across both drives. It's half the time because half the file is going to one drive and half is going to the other at exactly the same time. So you end up getting better performance with RAID. And that's an oversimplification of RAID. That's kind of an example of what RAID can be used for. So that was the server side of things. We can improve performance there, but what if that's not where the bottleneck is? How are we doing? Everybody's ready to run out and design a network and buy all this stuff and implement it, right? This is cool stuff. Improving circuit. I know, it's just I'm a geek. Improving circuit capacity. Upgrade to a faster protocol. That's kind of hard to do. Why? TCP/IP. It's the standard. We may not have the option of changing protocols. But if we're talking about the actual network cards, we can upgrade, say, from 100 base T to, or excuse me, from 10 base T to 100 base T, or we can go from 100 base T to gigabit Ethernet. So we have the ability to using the same protocol, but a higher speed network card to be able to improve the performance of our network. Just keep in mind, when you do that, that may involve the necessity to upgrade your cabling as well. So that's a potential issue that you might have to deal with. Increase the number of segments to a server. What happens when we put too many clients on the same segment? We talked about this a little bit earlier from a different perspective. If everybody's talking, we can't all communicate at the same time. So if we can separate that out, where half the class is in one room and half the class is in another room, does that mean we can't communicate at all anymore? Not necessarily. We can still communicate, but it allows us to more easily handle the individual communications that are going on in those two rooms. So that kind of give you a network diagram here, where all of these different clients here are on the exact same segment. Even in the switched environment, when utilization goes up to 95%, the network starts to bog down, right? That's what we saw earlier. So we can actually segment that, put in a second network card in our server, and we can have, using a subnet mask, we can have one LAN here and one LAN here. If a client over here wants to talk to a client over here, it goes to the server, the LAN 2 network interface card on the server here. The server says, wait a minute, that communication's not on this segment. I need to forward it to this network interface card and direct it to the appropriate client on that side. So they can still communicate. It just allows that traffic to be separated out and reduce the load on the network itself. The other approach is to reduce network demand. And there's things that you can do to kind of do that. So you can adjust the server, make modifications at the server. You can make modifications to your network line, and you can reduce network demand. Those are the three basic things that you can do. But how do we reduce demand? We can move files to the client computers, or at least closer to the clients. Why is that a big deal? The closer it is to the client, the less network they have to access to be able to access their file. So that's a general concept that applies in networking regardless of whether or not you store files on an actual client or not. Let's say, for example, you're Microsoft. You've got servers all over the world. if you're working in, say, San Francisco, their main offices are in Seattle, you don't want to access a file that's in India. That's a long ways away. You'd rather access it closer by. So even if it's on a server, you want to locate those files closer to the end users. You end up with better performance and less access to the network. So you can move files closer to the clients. Install disk caching software on client machines. That can be risky, but the advantage to that is what happens is your local machine stores a copy of that file on it. It's not something you really have to manage. The disk caching software takes care of that for you. What happens, though, is periodically that cache becomes out of date. So the longer that, however you have that caching software set up to scan or look for changes, the more out of date that file is going to be. You see this used a lot when it comes to internet files, for example. AOL was famous for doing this, or infamous, depending on how you want to look at it. That you would access a web page and it would store that cache on your system. The advantage to that was once you went back to that same web page, you would not have to go back out onto the internet and actually download that page again. It's already loaded in your cache on your local machine. The idea is you have better performance that way. That file's local, it comes up much quicker. The downside is what happens when there's a change made back on the server. There's an inconsistency between your cache file and the original file that's out there on the web server. So that's one of the problems with cache, but it is something that you can use if you've got static files that don't change that often. It's certainly a good approach to take. Move user demands to off-peak times. It's easier than you might think. There's some things that you have to access when you access them. That just makes sense, right? But what about printing? There may be certain types of print jobs, say all print jobs that are over 50 meg. We're automatically going to send those to a print queue that prints after closing time. We're going to allow our print server to do that. That pushes off-peak print jobs, or pushes print jobs to off-peak times. So we're utilizing the network at a time when the network's not really being hammered by normal usage. Something else you might do, they talk about here, early in the morning or after lunch. Why? People go into their offices and the first thing they want to do is sit down on the machine and read email. They start downloading all their email, all the various attachments and stuff like that. Why don't you reschedule your workforce, stagger when they come in, 8, 9, and 10. So now instead of everybody hitting it at 8:05, they're hitting it at 8:05, 9:05, and 10:05. So it staggers when they're banging away at the network. So there's just some of the things you can do to kind of manipulate the network demand. So improving LAN performance, kind of a summary of that: increasing server performance, increasing circuit capacity, and reducing network demand. Those are the three general categories you want to keep in mind when we talk about LANs. Implications for management. Cost of LAN equipment is dropping quickly. It's always dropping. Computer technology in general drops quickly. So just because it's dropping quickly, what it means is you end up with a flood of different vendors trying to provide various pieces of hardware. Unfortunately, that doesn't mean that all those various vendors produce equal quality hardware or software for that matter. It makes it really hard for network managers to justify the expense of going with, say, Cisco equipment over some XYZ brand. But the reality is in a lot of cases you end up with much better performance in your better manufacturers. They use better quality components and their warranties tend to be better, and they tend to support their products better. So that's something to keep in mind, but it's difficult on network managers to be able to make that justification, especially in times like now when the economy is the way it is. General managers are looking for places to cut costs, and as a network manager, when you go in like you're supposed to with alternatives, they see cheaper, they think it's better, and so it can be tough. LANs are more common, they're everywhere. Your cars. I mean, you go into your car, your phone wants to sync up with Bluetooth. You go into McDonald's, Starbucks, the airport, airplanes. Networks are everywhere. And switched Ethernet is now a legacy technology. That's not correct. Shared Ethernet is a legacy technology. A few new products developed for it. We don't use shared Ethernet anymore, at least not in the wired world. When we get to wireless, we'll talk about that a little bit more. It has some similarities to shared Ethernet, but in the wired world, you don't really see shared Ethernet anymore. You probably end up spending more to get a hub than you would to get a switch, not because it's worth more, but because they're so hard to find. So unless you just have some kind of really weird implementation of something, you want to avoid shared Ethernet. And that is that chapter. So I think it's a pretty good chapter. This is one that I think you guys should be able to get through relatively easily. And I think conceptually, though there's a lot of material there, I think conceptually it's fairly easy and straightforward. What are the questions out of that chapter?